everyone. Let's go ahead and get started. So here we've got Alessandro, and I actually don't know how to say your last name.
Saccon. Yeah.
Saccon, welcome, and thanks for getting us started on the last session of the day.
Thank you very much, Hannah. Okay, welcome everyone. My name is Alessandro Saccon. I'm an assistant professor in mechanical engineering, Department of Eindhoven University of Technology in the Netherlands. My talk is about impact-aware robotics. And as you see from also from the subtitle, what impact-aware robotics is exploiting intentional collisions to speed up task execution and reduce energy consumption. I will show some videos to just to give an illustration of what we mean, and we start with a video that everybody has seen already. If I manage to do so, let's see if I click. Over here, yeah. So you see again this idea of bustle dynamic robots performing really dynamic motions, really change velocity due to impacts, and this is an example of indeed impact-aware robotics in the context of locomotion. But what I'm actually interested in, and what this talk will be about, is mostly also the other situation where we are interested in speeding up and exploiting impacts for manipulation. Okay, this is an example of something that a demo that we run at the European Robotics Forums actually yesterday, and started on Monday with this idea that we want to have robots being able to toss objects, grab objects to speed up the process. Okay, and this is an example that shows a video that shows actually how repeatable this kind of motion can be. So we run this test for 3 days, 8 hours a day, and to show that here there's quite a lot of impact occurring, but still the box always end up in the same place. So this shows that both release and impact dynamics can be extremely repeatable. Why do you want to do these kind of things? Well, the industry is quite interested because you can speed up the process. So if you have to unload, for example, a tote with object, you put it on a conveyor, really common. Actually, people are doing this. You can gain 10 to 20% of time if you can actually toss instead of placing. This is, you see on the left, the traditional way of dropping or placing on conveyor belt, and on the right, this example of tossing. So in this case, you gain a factor of 20%. So you can imagine that if throughput is of importance, being able to perform this kind of option is quite important. Again, you can have also dual arm manipulation. This is also a partner, European project that I'm coordinating, where this is looking at the problem of tossing objects with dual arm system. So no conveyor, no suction cup in this case, but really with this idea of exploiting impacts to speed up the process. So humans are really capable of dynamic interacting with the environment, and also dynamically interacting with objects and environment, as we saw. And we do it every day for run, jump. So this is locomotion, and grabbing and tossing of objects. So that things that you saw also in the videos. So the robots are not yet there, but they are definitely catching up, or at least we are making them catching up, developing more and more robots that are resilient to impacts, and new type of control and estimation strategy that can actually make this kind of action happen. So a new field, I would say, of robotics research is emerging, and this is also, what this workshop is about, and is really the focus on exploiting intentional collision for manipulation and manipulation and locomotion. So at least at the TUE, we refer to this type of research and application area as impact-aware robotics. Okay. So why this is relevant? This is what I was mentioning before. The standard way of picking and placing object is really moving fast, closing the gripper, and then move again. So you see this what happens in terms of the fact that you have to reduce the speed to 0, make contact, and so on and so forth. So it's not ideal in terms of time and energy consumption, but we know how to do it. So this is the standard way of doing it in industry. Well, in principle, you will like just to have really fast grabbing motion. I saw also today in some of the poster session, this idea of being able to have robots doing this kind of motions. And of course, this will reduce both time an energy consumption because you don't have to decelerate and accelerate again. But we don't really know how to do this. I mean, of course, well, you see Boston Dynamics can really do it for locomotion, but there's plenty of things still to do in terms of manipulation in particular. So what is the problem? What is missing? So the thing is that if you have a robot interacting with an object that is relatively heavy, and the moment you have contact, there's a lot of dynamic interaction happening between the object and the robot dynamics. In particular, the state of the robot in terms of velocity is changing extremely fast. So if you want to have a robot doing this, they need to be able to predict what is going to happen in many, many different situations at the moment of establishing contact. So one has to study and really do experiments and validate, what kind of model you can use to predict the behavior. And of course, there's also an idea that you plan a motion, but then typically things will never happen as intended, especially in the moment of having the impact time. So there is somehow a mismatch. And this creates also an issue of how to define a tracking error for really executing this motion, okay? And not only that, if you have, for example, multiple hands or dual arm kind of a system I was showing before, you might have an intention to touch at the same time, to having really nice and flat, contact. But then when you execute it, all kind of things can happen. Usually you might have a problem with perception. You think that the box is, for example, 0.5 centimeter on the side, and you will have all kind of situations where you impact on one side and then the other. So your intention is to make impact simultaneously, but when you execute it, this never happens. And so this somehow you need to understand also what does it mean to do feedback control in this situation, due to the presence also of somehow intermediate impact phase that cannot really be predicted or even understood at the execution time because they happen too fast. So you also have to, if you want to perform this kind of motion, it's better for you to have systems that really understand if something is not going well. So you need to have some collision monitoring that are really aware of what is the aim you want to achieve, and if something happens, the object starts slipping, or somehow you wanted to have a system running on a floor, then they assume that there was quite some grip, but then there's some soap or maybe it's icy, and then you want to very, very quickly figure out if things are really different from what you expect. Then there's all the question, okay, if I have to do something motion, you need to have planners. You have to figure out, okay, what is the best posture that I have to have on the robot in order for performing maybe the best in terms of energy consumption or speed of execution. So some form of motion planning. And of course, then you can think of all kind of learning. So you want to execute maybe many times or demonstrate all this kind of operation with for example, in teleoperation. And then the question is, okay, what should you learn? Because there are these big discontinuities and this big mismatch. And so that there is a question of what really you should learn from this motion. And of course, you need all kind of software that all put together in order to integrate all this functionality. So suitable hardware is definitely becoming available, but there's still ample space for improvement. In any case, the focus for me and also in the last years has been really understanding how we can put together a theoretical framework and software for this kind of operations. So, like I said, there are many aspects you can consider in this talk. I will just mention a little bit about how to handle time mismatch and how to deal with the ideally simultaneous impact, where the intention is to, for example, having contact at the same time, but then how to handle this uncertainty that you might touch the object only on one side, or and how to make this kind of motion robust. What can happen or not. So for this, we in the previous starting from 2014, I would say, we started proposing an idea which is called reference spreading, and I just want to give a bit of a really simple idea, just to what the problem is, and what the kind of solution we are using, and how then we redefine this also not only for the time mismatch, but also in the presence of this idea of having simultaneous impact. So this is the typical situation. You would like to have some form of a very fast motion. Then at the moment of contact, somehow the robots and object dynamics have a discontinuity. And so this is your intention. Right? So then when you try to execute this motion, what typically happens is that you have impact at a completely different time. So if you want to build a controller, then there is a problem that this mismatch is creating, that if you actually computing an error between this signal and the signal that you have as an intention, you create an extremely large error that can then cause unintentional harm to the robot and the system, because simply you compute a large error and that creates also an extremely large torque on the system. So what we proposed with this idea of reference spreading is simply to say, well, instead of having just one reference, nominal reference, you can actually extend, like if you want to have contact, you cannot pretend that the object is not there. You just pretend that there's no surface. You continue on this type of trajectory. And for the motion after the contact, you can actually imagine that the contact was established before, so you can actually extend backward in time. So this simple idea has quite a lot of consequences. And in particular, you can now do something which is very interesting, that you can actually compare, especially in this case, because the impact occurred before, you can actually compare this trajectory with this extended trajectory backward in time. So the error in this case is fairly small, and this will also imply that the kind of signal that you give as a correction is quite limited. So you won't have this issue of peaking that is well known, at least for the people that have been working on this field. So we tested all this. This is sort of a history of the idea on a really simple system. To start with, a one-off system. This is called an actuated and abandoned pendulum, where essentially you want to have a motion that where as the pendulum is moving and you impact on the surface. Just to give you an idea of what happens when you try to apply the standard trajectory tracking without doing any extension. What happens is that you would like to have a particular motion of the pendulum, which is sort of a light blue here. And you can use a standard PD controller, and you see that if you use really low gains, typically you have really poor performance because of the fact that impacts occur at the time that is not corresponding to the motion you wanted. So suddenly, because you impacted before, you are still following the trajectory, the nominal trajectory that's telling you that you should have an impact again. So you have a really strange behavior, and then it's really hard to track the trajectory. On the other side, if you try to crank up the gains and increase them, what you see is that, yeah, you will converge to the trajectory, but typically then you have really large torques due to this error that is quite large due to the time mismatch, and for that results in a really large torque. So if you just change the way you define the error, then you get a way better performance, also for low gains. This is the picture that is showing here, but you still have problems with for example, with the torque at the impact time. And this was somehow surprising at the beginning, but then it turns out that this is just due to the fact that you are not using a very good state estimator for the velocity, because of course the velocity estimated from an encoder, and if this is really a jump, somehow you are not really estimating the velocity, because you're estimating you're using essentially a low pass filter. So as long as you create an advanced velocity filtering that actually can estimate the velocity right after an impact, then you recover this idea that for any type of gains that you use, you still have pretty much what you expected in terms of torque. And the result is a impacting motion like the one that is shown here. But okay, I just want to play it just to show you. But in any case, this is a fairly simple situation, but show the potential of this kind of technology just by changing the way you define the error tracking for a system with impacts. So this was a few years back when I was actually one of my first PhD working on this field. And then we proceed. Okay, I got a grant where we actually look at how to use this kind of technology in the context of logistics. So we want to have robots picking up boxes, like you see, or robots placing them, on conveyor. We have, 4 industry partners and 4 academic partners that are looking at this problem. So one of the things I want to mention, we just have 15 minutes, is that we are also refining this idea for a situation where you have, like I said, a situation with multiple contact points. In this case, there's a robot that has to push a door, and we extend this idea of reference spreading not only for a trajectory, but we essentially have a pre-impact motion and a post-impact motion. So you want the robot essentially to push on this door and then end up in a final situation. But because of the fact that you might have some misalignment, you might end up in a mode internally that needs to be coupled. So this is somehow also similar to the situation of impacting only on with one hand instead of both at the same time. So what is really interesting is that in the change is really to be able to have an intermediate controller that takes into account the fact that during this intermediate mode, it's not really a good idea to try to use any velocity feedback. But actually, it turns out that it's quite interesting that you can actually use position feedback in that case. Details, I mean, you can see in this paper that we already submitted. But the idea is that essentially by doing this, you can guarantee that the motion is actually executed. You jump between the two trajectory in terms of position, velocity, and orientation. And what it's quite interesting to see is that if you would use something that is not aware of this impact occurring with the state, or you just use a previous version of the controller that just jumped one time, actually the kind of torque you get in this situation are completely different. So the one we actually proposed shows that the motion is the same, but in terms of torque and force you are applying on the system, you get quite smaller requirement. So what we are after, well, we are now using all these ideas to show that we can actually perform this kind of motion, at least in simulation, making use of a physics engine that has been developed by one of the partners, but this is the vision to be able to perform this kind of motion. And we already started testing this kind of concept on also in collaboration with Jens and here at TU Delft, with the idea of showing that using or not this intermediate mode has a benefit in terms of the kind of torque and forces you see and exert with the environment. In this case, you see that when try to perform this motion with sliding, having an intermediate mode that is active when you are in this phase can have quite significant contribution in actually the type of peak force you apply on the environment. Okay, so in terms of motion, the motion is quite similar, but in terms of force, there's a large difference. And at the moment, we are busy with try to implement this now on a real system. And I think with this, I would like to conclude and take some questions.
Great, thank you. I'll ask the next speaker.